Hello everyone, and welcome to this Channel Talent headliner on mathematical modelling with sequences and series. My name is Dr. Robert Whittaker. I'm a mathematics lecturer at the University of East Anglia, and this is a picture of our beautiful campus on the edge of Norwich. Do check us out if you want to know more. Okay, so today I'm going to be telling you about a mechanics-based problem, but it's a problem that leads to some interesting pure mathematics. It will be really useful if you could get hold of a set of sort of identical blocks, a bit like this to play with. So these are from a giant Jenga set. You probably need 6 or 7 of them. They all need to be the same size and shape and mass, but anything similar will do. You could use ordinary Jenga. You could probably get away with dominoes as well. But it'd be good if you had some of these to have a play with in a moment. It would also be useful if you could pause this video halfway through to try some of the things I'm going to suggest, and then come back and watch the second half, and then I'll give you a few more things to think about before the live session later on. Okay, so what are we going to be talking about today? Well, it's a problem creating a leaning tower made from these identical blocks. So we're going to have a setup as follows, as you can see in the picture. So we're going to have a base block, and then on top of that we're going to stick n other blocks, one per layer. So with n equals 2, it might look something like this, but n could be any positive integer. So there's 3 blocks on top, 4 blocks on top, etc. So for any n you want, you have n blocks stacked on top of a base. There's exactly 1 block per row going up the tower, and each block is slightly further to the right than the ones below. And the aim is to build something that's leaning, but is freestanding. So there's no glue. These have all just got to be balanced under their own weight. And you can see that if I move them too far, it's going to overbalance. So I've got to not go that far and come up with some stack that just balances itself. And what we're interested in is how far over can you get this leaning with a given number of blocks. So let's introduce a little bit of notation. So we've already got that the number of blocks above the base is n. So we'll have some notation for the lean or overhang. We'll call that S, and we'll say that's the horizontal distance from the right-hand end of the top block to the right-hand end of the base at the bottom. So this sort of distance across here from the base to the edge of the top block. And what we'd like to know is for a given n, how big an S can we get? What's the maximum value of S that we can have for that n? And then also how that value of S depends on the number of blocks n. So you might think that as we add more blocks, we'll get a larger S. But what sort of relationship is there between the maximum S and the number of blocks n? So hopefully you've got some blocks that you can play with, and I'd like you to, if you can, have a go at answering some of these questions. So try stacking the blocks up by hand, have a play, get a feel for how far you can move them and still keep it balanced. And one question to ask yourselves is, can you get a stack in which the top block completely overhangs the base? So I want this left-hand edge of the top block to be slightly further to the right than the right-hand edge of the base here. So in this stack it's not going to work, but maybe if I rearrange the blocks or if I added more blocks, I would be able to get it to balance with a complete overhang. So can you do that? And if so, what's the minimum number of blocks that are required to do it? And if you've got enough blocks, how large an overhang can you get? So could you get this top block sort of 1.5 blocks away or 2 blocks away even, if you had enough blocks in your stack? And one hint as you're playing with these is to work from the top down. So if you can get the top block just balancing by moving it, and then take the top 2 blocks and move them, you won't affect the top block balancing as long as you keep the top 2 in the same relative positions, but you could move them as a block and get them balancing and then move the top 3, etc. And that's an easier way of getting to the maximum overhang. If you haven't got any blocks, then don't worry, there are also some other things for you to think about. So we don't just want to play with the blocks, we also want to think about this problem mathematically. Um, so how might we do that? And I'd like you to think about the following. So what properties of the blocks do we need to know in order to be able to calculate the overhang? So what's important about each block that we've got? How are we going to describe the position of each block so we know what the stack looks like? So how far to the left or right is each block, and how are we going to record that mathematically? We also need a way to tell if the stack of blocks is balanced. So um, given the positions of the blocks, how can we tell mathematically if that stack of blocks is going to be stable? And finally, what we'd really like is some sort of formula that gives us the maximum lean or overhang S as a function of the number of blocks n. So can we come up with some sort of formula for Sn? So I'd like you to have a go at those. If you can, pause the video, have 15-20 minutes if you can, playing around with the blocks, thinking about these questions about the modelling, and then come back and watch the second half of this video. Okay, so welcome back. I hope you had a bit of fun playing with the blocks. I'm now going to go through some of the things that hopefully you managed to discover for yourselves, and then we'll talk a little bit about the modelling, and then I'll set you some more challenges to think about before the live session. Okay, so if you've been playing with the blocks, you've hopefully found that stacking from the top works. We could start off with 2 blocks and get that just on the point of balancing, like so, and then take that stack as 1 unit, put that on top of a 3rd block, and again move that until it's just on the point of balancing, and then take that stack of 3 as a unit, put that on top of the next block, and keep going like that. And we don't have to do anything with the top blocks, we only have to move the whole lot as a unit backwards and forwards and get it just on the point of balancing, and that will hopefully give us the largest overhang we can. And if you've been really careful, you should find that with 4 blocks above a base, so for n equals 4, you can just about get the top block to completely overhang the base. I think I might have just about done it there. You can certainly do it with 5 blocks above a base, that's much easier. You've probably also noticed that as you're stacking them up like this, the overhang you get with each additional block is going to be smaller than the one before. So whatever overhang you're getting for S, it's going to increase more and more slowly as you increase N. Because of that, I don't think it's really obvious whether there is a maximum overhang you can get or not. You're sort of adding on smaller and smaller bits, but does that mean that the overhang just gets larger and larger but more and more slowly, or does it approach some finite limit? And that's something that we're going to think about theoretically with the mathematical modelling later on. And then finally, in terms of balancing, the criteria for the stack to balance is that for each set of blocks taken from the top, you need that set to balance on the block below. So the first block needs to balance on the second block, the first 2 blocks together need to balance on the 3rd block, and the first 3 blocks need to balance on the 4th block, etc. And if that's true for every set of blocks taken from the top, then the whole stack will balance. Okay, so that was playing around with the blocks. Now let's think about the mathematical modelling. So I asked you to think about a few things. So first of all, the properties of the block. Well, in terms of making the stack physically, we might need to know about the dimensions of the block. So we're just looking at 2D essentially in this stack. So we need to know the length of the block. Let's call that L. Maybe the height of the block H. And also the mass of the block M might be important as well. So let's introduce variables for those 3 quantities. We're assuming that all the blocks are the same, so we'll just have 1 mass, 1 length, 1 height that's going to apply to each of the blocks. In order to record the positions of the blocks, we're going to need to know which block is which, so we need to label the different blocks. There are n blocks above the base, so let's number them from 1 to n. And because we found it was convenient to start stacking from the top, it's probably a good idea to number them from the top as well. So we'll say that the top block is number 1, then number 2, then number 3, then number 4, and so on until we get to the nth block, which is just sitting above the base. And having numbered the blocks, we can then think about their positions. So we need to record the position of each block somehow relative to the base. And you might think it's a good idea just to record the horizontal displacement of each block from some fixed point, say on the base. Actually, it turns out it's a little easier to think about the overhang of each block relative just to the block below. So we'll have a whole set of overhangs recorded, one for each block, and we'll call them A1, A2, A3, A4, etc. And A1 will be the overhang of the top block, so this distance here. A2, the overhang of the second block. A3, the third block, etc. So if we add up all those overhangs, that will give us the total lean S. So Sn is going to be A1 plus A2 plus A3, etc. up to AN. And there's some nice sigma notation that you may have seen in A-level maths. We could write that as the sum from k equals 1 to n of AK. And then finally, the condition for stability or balance. For each k, we want the set of the top k blocks to be balanced on the block below. And physically, that means that the center of mass of those k blocks, taken as a single unit, needs to be the right side of the edge of the block below. So if the center of mass is to the left of the edge, then it's going to be balanced. If the center of mass is to the right, then it's going to topple over like that. Okay, so that's a bit about the mathematical modelling. There's still a little bit more work to do because we need to interpret this balance condition and work out what the AKs can be in order to get our final formula for the SM, but it's at least a start, and we've now got some notation and some variables that we can work with. Okay, so there's some more challenges now for you to think about before the live session. So first of all, if you're into mechanics, you could have a go at proving that for a just balanced tower, each of the overhangs, AK, are equal to L divided by 2K. So for K equals 1, you'd have an overhang of L over 2, and maybe you can see that's what's got to happen. And then for K equals 2, you'd have an overhang of L over 4. And maybe that's obvious as well, but can you prove that for a general K? And then if we've got that formula for AK, we can put that in and we've got a result for Sn now. And then using that result, theoretically, we can answer a number of other questions. So can we find theoretically what the minimum number of blocks n is, such that the overhang Sn is greater than L, and that corresponds to the idea of the top block overhanging the base completely. So can we find theoretically the minimum m and n, and does it agree with what we did experimentally earlier? And then we could ask, well, is it possible to get an overhang that's 2L? So we've got the top block sort of a block away from the bottom block. And if so, what value of n is needed? We could also think about this formula for Sn and say, well, what happens to Sn as n tends to infinity? So as n gets very, very large, how does Sn behave? And finally, maybe someone challenges you to create an overhang of a certain amount. Could you estimate how many blocks, how big an n you might need to achieve that? And maybe if you think about the behavior of the formula for Sn, you may get some ideas as to how big an n you might need for a given overhang. Okay, so try and have a go at those if you can before the live session. And one little hint for you that might help you with number 1 is to do with centers of mass. So if you've got two bodies and you know what their masses are and you know what their individual centers of mass are, there's a formula for working out what the center of mass of the combined body is, and that might be useful in order to prove the overhang for a general K. So I'll leave those ideas with you. Do have a play around, and I'll look forward to seeing you in the live session on Channel Talent.